Forgot to do that. Okay. All right. So today we're just going to cover one pretty brief topic. It's called concentration of solutions. So this is the final section that we have to work on for chapter 4. And then next week we'll work on chapter 5. So concentration of solutions. So we're going to begin with a little bit of terminology here. So when we consider mixing things together, let's imagine that we're going to use water as the liquid that we're going to dissolve things in. So water is what's called a solvent. And the solvent is the substance that dissolves other substances. And those other substances are called solutes. So the solute is the substance being dissolved. Okay, so the solute is what gets dissolved. The solvent is the substance that's dissolving it. And together, if you mix the solvent plus all of the solutes, so you could have more than one solute, right? So you could have salt and you could have sugar dissolved in water, so solutes. Together, we call that a solution. Okay, and it's a type of mixture. So imagine that we take something like sodium chloride, salt, right? So salt is a solid, and we dissolve it into the water. So we add it to the water, we mix it. What's going to happen is the salt is going to dissolve into the water. And so that water will now become a little more dense because it has this extra mass of sodium ions and chloride ions, right? So we now have a mixture, a solution. If it's well mixed and you can't see any particles floating around in there, we would call it a solution. Okay. So what we're going to do in this particular topic is we're just going to look at how we calculate how concentrated those solutes are. So it's concentration that we're concerned with. So there are different ways to define concentration, but one way is to say that concentration is, I'm going to write it as an equation, the amount of a solute, all right, so the amount of sodium chloride divided by the amount of solution. Okay, the amount of how much of this sodium chloride you're putting in divided by the amount of the solution. And as I said, there's other definitions we could use, but that's what we'll use for this discussion today. Okay, so amount of solute. Now, amount is that's ambiguous, right? What does that mean, amount? Are we talking about the amount of mass that you have, the amount of space that you're taking up, the volume? What do we mean by amount? And so that's where the details get into play. We're going to use for this section one specific type of concentration, and it's called molarity. And you would pronounce it kind of like density, molarity. Molarity, the abbreviation for it is a capital M, not a lowercase m, but an uppercase M. And this is defined as the moles of the solute divided by the volume, the liters of solution. Okay, so it's the number of moles of this. How many moles are we putting in, right? So it might be 1 mole, might be 2 moles, might be 0.2 moles. So how many moles of that are we putting in? Divided by the volume, divided by the liters of solution. So notice it's not milliliters, it's liters, okay? And so the that comes into play that 1,000 milliliters is equal to 1 liter. Okay, so 1,000 milliliters. Remember, a milliliter is the same thing as a cubic centimeter. So 1 milliliter is a centimeter cubed, or a cc. Sometimes we call it a cc. It's all the same thing. So if that's true, then we could also say 1,000 cc is also equal to a liter. Okay. So when you buy a small bottle of water, you know, the ones that are about that tall, it's like a pint. That's roughly 500 milliliters. So it's half of a liter. And then a liter is a little bit bigger one, right? And then you have the 2-liter ones as well, right? So, you know, 1,000 milliliters is a liter. So it's important to note that we have to have the units in here in liters, and we have to have the units here in moles. There's a couple of exceptions to that. Sometimes what you can do is little tricks. So for example, if I had millimoles, if I knew the number of millimoles and I knew the number of milliliters, I could just cancel the millis because that would give you moles per liter. So if you have millimoles and you have milliliters, then you don't actually have to convert them to moles and liters. You can leave them. But you can't do that if they're different prefixes. So for example, if you had micromole and milliliter, you can't cancel a micro and a milli. They're not the same thing. So for that case, we'd have to maybe convert this to milli, or convert it to just moles and convert this just to liters so that we can do the calculation. But the definition of molarity is moles per liter, okay? So it's the number of moles divided by the volume. There are other concentration units out there. There's molality, there's mass percent. In the vinegar titration experiment, they actually have you calculate the mass percent. There's osmolality. That's another form of concentration, I guess. Osmolality is perhaps. But there's mass volume concentrations. There's volume concentrations, mass percent, mole fraction. That's another one as well. So there's many different concentration units used. However, for us, the one that we're going to be concerned with today and in this chapter is this one here, molarity. I find it useful to write it in abbreviated form. Capital M for molarity equals N for moles and then V for liters. So this has to be in moles, this has to be in liters, and then this is molarity. The reason I find that useful is because if you know two of them, you can calculate the third very easily, right? So it's analogous to density equals mass over volume. That's an easy equation to use. So you can kind of use this one in the same way, okay? So let's take a look at an example. Let me just stop this screen share here and let's share this one. Okay. There we go. So calculating the molarity using solute moles. So in this one, they're going to give you the moles of the solute. So a chemist prepares a solution of sodium nitrate, NaNO3, by measuring out 87.6 micromoles, see the micro symbol, of sodium nitrate into 300 milliliters, a 300 milliliter volumetric flask, filling the flask up to the mark with the water. Calculate the concentration in moles per liter, that would be molarity, of the sodium nitrate solution, okay? So let's talk a little bit about what a volumetric flask is. Some people have used them in labs. A volumetric flask typically has a long neck, which is called a stem. And then it flares out to have a volume, a large space. So it's a container for liquids. Okay, it might look something like that. It also typically has what's called a stopper. So it has this either glass or plastic stopper that you can put into here just to stop it, right? So it's just a way to plug it up here at the top. There's also a marking that's made in the factory, and it's like a little circle that goes around the neck. And then what happens is when you purchase them, they are calibrated for a specific volume. So in this particular problem, they're saying it's a 300 milliliter flask. So what that means is if you fill it with water, you know, so you're adding water to it, up to this little mark here, up at the top, this marking or etching, so the meniscus fills in like this. What we would say is this now has 300 milliliters of solution in it. Okay, so there's your 300 milliliters. And you can buy one, you know, I've actually never seen one that's 300, but you can buy them at 250, you can buy them at 500, you can buy them at 100 milliliters. They usually go, you know, 1 milliliter, 2 milliliter, 5 milliliter, 10, 25, 50, 100, 200, 250, 500, and then 1,000 milliliters. But in this particular problem, it's 300 milliliters. Okay, so in this problem, they're telling you that the volume is 300 milliliters. Okay, they're also telling you that you have 87.6 micromoles of sodium nitrate. Okay, so that's the solute. When they give you the number of moles, that's referring to the solute. The solvent is water. Okay, so when you mix everything up, the sodium nitrate with the water, and you fill it up all the way to the 300 milliliter mark, there's going to be a certain concentration of sodium nitrate. Okay, so what we want to do now is we want to calculate what is that concentration. It's very simple. The molarity is the number of moles of the solute divided by the number of liters of solution. So we just have to get the units in the right place here. So it's 87.6 micromoles. We want to have that as moles, not micromoles. So we have to get rid of the micro. So here's how we'll do it. 87.6. What is micro? Micro is 10 to the minus 6. So that means it's 10 to the minus 6 micromoles. So now it's in moles. Notice it's not in scientific notation. Scientific notation is a number between 1 and 9 times 10 to the x, where x is a whole number. This is 87, so that's, you know, not between 1 and 9, but that's okay because it's not our answer. You know, generally you want to have numbers in scientific notation if it's your answer, but it doesn't have to be if it's in your calculation. So we know the number of moles, 87.6 times 10 to the minus 6 moles. Divide that by the number of liters. So that's your solution there. But it's not in liters, it's in milliliters. So what do? We say, hey, 300 milliliters. Okay, what is milli? Milli is 10 to the minus 3. So that would be 300 times 10 to the minus 3. 300 milliliters. And then if you want, you can play around with the powers of 10. You could cancel out, you know, 10 to the minus 3 from the numerator and the denominator, but you don't really need to do that because you can just plug these numbers right into your calculator. And that's actually pretty straightforward. So you just take your 87.6 times 10 to the minus 6, divide that by your 300 times 10 to the minus 3, and you get a pretty small number. It's 2.92 times 10 to the minus 4. And then the units are moles per liter. Okay, so strictly speaking, those are the units. You will see it drawn. People will write it this way. They'll just write 2.92 times 10 to the minus 4 molar. The way this is pronounced is molar. Right, like a molar. There's a tooth, right? There's a molar, premolar teeth, right? So this is molar, meaning moles per liter. Okay, so capital M is the abbreviation, but the actual units are moles per liter. Okay, so that's a pretty small number. It's not very concentrated. So let's take a look at another example.
How did you get them -4?
I plugged it into the calculator.
Okay, thank you.
Mm-hmm. Okay, so here's another. Let me share this one. Okay, this is kind of the same thing, right? They give you the units in micromoles and milliliters, so it's really not all that different. It's really just the same thing. Same thing. So these are all micromoles and milliliters, so they're all about the same. So let's take a look at this one then. This one is a different substance. It's iron 2 bromide. The concentration is 4.4 times 10 to the 2. So that's a larger amount, but it's in micromoles, and then you're going to divide that by the volume. So let me, let's go over this one. Just show one more. Okay. So you've got, for some reason, I always go back to that one. So you've got 4.4 times 10 to the 2 micromoles. And that's the amount of iron bromide that you're putting in there. So it's dissolved in the water, and then you've got 500 mil. Now notice the 500 is the volume of the solution. Okay, so let's take a look at this one. So you got 4.4 times 10 to the 2 micromoles. Again, you want to make it sure it's in moles. It's got to be moles per liter, not micromoles per liter, right? And not micromoles per milliliter. So micros 10 to the minus 6. So 4.4 times 10 to the 2. And then micros 10 to the minus 6. And then that's moles. So now you got this weird number, right? 10 to the 2, 10 to the minus. What do? Remember, when you multiply powers of 10, you add the exponents, right? So you just add them. So for example, 10 to the 2 times 10 to the minus 6, you just add these two numbers together, so you get 10 to the minus 4, okay? So now you've got 4.4 times 10 to the minus 4, okay? And then that's in moles, right? Okay. And then let's do the milliliters. So you got 500 milliliters. We're gonna divide this by the volume, right? So 500 milliliters. Milli is 10 to the minus 3. So that's 500 times 10 to the minus 3 liters. Okay. Now you can actually do a lot of this without a calculator, because what you do is you say this. If I put this in the one in the bottom, if I put it in scientific notation, you move it over 2 places. And when you move it to the left, this exponent becomes more positive. So you get 4.4 times 10 to the minus 4. So if you moved it to the left by 2 places, it becomes more positive. So minus 3, minus 2, minus 1. Okay. So that kind of simplifies it a little bit. Now what you can do is you can say this. If I have 10 to the x times 10 to the y is equal to the 10 to the x plus y, then I can also say this. 10 to the x over 10 to the y is 10 to the x minus y. You can combine those if they're the same base. So what you have here is 10 to the minus 4 over 10 to the minus 1. So that would be 10 to the minus 4 minus a minus 1. You take the one in the top and you subtract the one in the bottom. So minus a minus. Well, minus a minus is plus. So that's 10 to the minus 4 plus 1, which is 10 to the minus 3. So this is really then, you can simplify this as 4.4 over 5.00 times 10 to the minus 3, and then the units are moles per liter. Okay, so now you've got a number 4.4 divided by 5. So 4.4 divided by 5.00, now you have 0.88. So this would be equal to, I'm going to move it up here. This over that is 0.88. And then you just have your 10 to the minus 3. We can clean that up. What you do is you say, we want it between 1 and 10 or 1 and 9. So you move it over to the 1. You move it over one spot. And then if left is positive, that means right is negative. So this becomes more negative. So minus 4 moles per liter. Okay. Seems a little low, but I guess that's right. Yeah, I think that's right. Because it's really 4.4 times 10 to the minus 4. Yeah. Yep, that's right. So there's your right answer. Okay, so there you go. All right. So you can either do it in your calculator or you can go through and do the exponents in your head or on a piece of paper and then clean it up a little bit and you get your answer. Okay. So that one is pretty straightforward because all they're doing is they're giving you the moles and you're giving you the liters. They're giving you both of those units. You just have to do the unit conversions and then you're taking the ratio. So think of concentration as the amount of one thing divided by the other amount. So it's the amount of what of the salt you're putting in divided by the total solution. Units are moles per liter. The
I have a
second
question.
Yeah, go ahead.
So at the top here, 4.4 times 10 to the negative 4 moles over 500 times 10 to the negative 3. Is there a reason you put, when you said that the decimal should be 2 over, shouldn't it be 3 over? Shouldn't it be 0.5?
Oh, let me see. Let me come, okay, so let me take a look at that. Let me make a little room over here. You might be right. So let's see. Okay, so we got 4.4 times 10 to the minus 4 over 5 point, well, it's 500 milliliters, right? So 500 times 10 to the minus 3. Okay, oops. 10 to the minus 3. So 500 times 10 to the minus 3. So what another thing you could do is this. You could say, move this over to the left 3 places, and then this is going to increase 1 digit every time you move it 1. So if you move it over 3 times, 3 spaces, 3 digits, that will get that up to a 0. 10 to the 0 is 1, right? So this could also be written as 4.4 times 10 to the minus 4. I'm going to move it over 3 places. That gets rid of this 10 to the minus 3. So you have 0.500, right? So that would be another way to do it. So now, now this is pretty cool because now you're just dividing by 0.5. Remember, if you're dividing, if I take a number and I divide it by 0.5, that's just going to be equal to 2, right? You're just going to double it. So it would be 8.8 times 10 to the minus 4 because we don't have any exponent down here at all. And that's actually an easier way to do it, actually, now that I think about it, right? That would work as well. Yeah.
Awesome. Thank you.
Mm-hmm. Yeah, these exponents are cool. That's actually the, one of the reasons we use scientific notation is because the exponent is, an exponent is really telling you how many zeros are in the number, right? Like, so if I say I have 0.00001, right? We're representing that as 1 times 10 to the minus 5, right? Or you could even just write it as 10 to the minus 5. So the cool thing about that is that if you're taking these numbers and you're multiplying them, so like if I multiply those, look at all those zeros, what do? Well, if you just say this is 10 to the minus 5 and this is 10 to the minus 2, the rules of exponents is that if they have the same base, 10, then you just add the exponents and you get 10 to the minus 7. So it's just a way to kind of cut through all of the, the powers of 10 and stuff like that. It's a nice notation. Okay, so let's take a look at solute mass. So the second type is where you're doing solute mass. So they're not going to give you the number of moles. They're going to give you the mass of the solute. Okay. So here's an example. Calculating molarity using solute mass, right? So they're not giving you the moles, they're giving you the mass. So a chemist prepares a solution of copper 2 fluoride, which is CuF2, by measuring out 0.0558 grams of copper 2 fluoride into a 400 milliliter volumetric flask and filling the flask to the mark, right? So they're filling it up to that mark, okay? Calculate the concentration in moles per liter of the chemist's copper 2 fluoride, rounded to 3 sig figs, right? So again, concentration in moles per liter, right? Different chemists will use different units for specific types of problems, but in general, the most common form of concentration is moles per liter. So that's why this section is focused on moles per liter, okay? So let's take a look at this one. There we go. So the amount they give you is 0.0558 grams of copper fluoride. And they tell you the volume is 400 milliliters. Okay, so same thing here, right? You got the milliliters, so you're going to have to convert milliliters to liters. That's just like we just did. The issue here is that this is in grams, so you got to convert it to moles. So there's an extra step here, right? We want moles of copper fluoride, not grams of copper fluoride, okay? So how do we do that? Well, we use the molar mass, right? This is a mass to mole conversion, back from chapter 3. So we're going to divide by the molar mass. Now, technically speaking, they'll call it the formula mass. They won't call it the molar mass because copper fluoride is an ionic compound. Ionic compounds, we use the term formula mass, but it really is the same thing as the molar mass. So let's figure out what the molar mass of copper fluoride is. Okay, we got 1 copper. So that's 63.55 grams per mole. And you got 2 fluorines, so 2 times 19. Right? So 1 copper, 2 fluorines. So 63.55 plus 38. And you get 101.55 grams per mole. So there's your molar mass. So now we just do our little conversion here. So 0.0558 grams of copper fluoride, copper 2 fluoride. 1 mole of copper 2 fluoride weighs 101.55 grams. Okay, so you're just going to take your 0.0558 divided by 101.55, and you get, it's a pretty small number. I'm going to write it in scientific notation, 5.495 times 10 to the minus 4 moles, right? It's moles because the grams cancel and you're left with moles. So we divide it by the molar mass, okay? Now, what about our volume? Well, same thing, 400 milliliters. You know, if you want to do it this way, 1,000 milliliters, I'm sorry, a liter is 1,000 milliliters. I keep doing the same thing. 1 liter is 1,000 milliliters. So you're dividing by 1,000, right? So you get 0.400 liters. Or you say 400 milliliters is equal to 400 times 10 to the minus 3 liters. And if you want to get rid of the scientific notation, move it to the left by 3. That increases this by 3, which gives you 10 to the 0, which is equal to 1. And you get 0.400 liters. So same answer either way, right? So you can either use the 1,000 milliliters per liter, or you can just put it in scientific notation, and that'll give you the same answer, okay? So now we want to divide moles by liters, right? So let's do that up here. Okay. 5, so our molarity, capital M, would be 5.495 times 10 to the minus 4 moles. Divide that by your 0.400 liters. Okay. Dividing by 0.4 is like dividing by 2/5, So it's like multiplying by 5/2. So you're going to take that number in the numerator and multiply it by 5/2. And you get, it's still a pretty small number. I'll put it in decimal notation. Okay, it said to put it in 3 sig figs. So remember, the leading zeros never count as sig figs. So zeros count if they're captive, if they're in between numbers, and they count at the end if there's a decimal point, but if they're in the front, they never count. So those first 2 zeros don't count. If we want to put this in scientific notation, you go 1, 2, 3. So that's 1.37 times 10 to the minus 3. Remember, left is positive, right is negative. So if you're moving the decimal point to the right, the power of 10 becomes more negative. So -1, -2, -3. So again, small number, right? That's a small molarity. Molarities are usually pretty small. If there's a limit to how much stuff will dissolve in water. So you can't put 55 grams of copper fluoride into water, into 400 milliliters of water. It won't dissolve that much. So you're not going to get like 1.37 molar, 1,000 times greater. You're going to get them less than 1 for most of these. There are some substances that you can dissolve. Sugar dissolves in a high concentration. Sodium chloride actually dissolves, but you're not going to get 1 molar or any higher than that. It's going to be small numbers like this. There's just a limit to how much you can dissolve into the water before it starts precipitating out. If you keep adding, so actually I was watching someone make like Kool-Aid the other day, and they added so much of the powder to the water that it precipitated down at the bottom. So you had the sugar with the dye at the bottom, it didn't dissolve. That's not a solution. It's a mixture. You've mixed those things together, but we cannot call it a solution, because to be a solution, the solutes have to be evenly distributed throughout the mixture. And when you have a solid down at the bottom, that's not the same as having it dissolved up at the top. That's not an even distribution. So we would call that a mixture, but we would not call it a homogeneous mixture. A homogeneous mixture is a solution where everything is the same concentration throughout. Okay. So yeah, there's a limit to how much of these things you can put in. Even the most soluble salts have a limit, right? At some point, if you keep adding more and more and more, you'll eventually have more salt than you have water, right? So like if I take a big bag of salt and put it into a little bit of water, what does that do? The water is no longer acting like a solvent anymore. And so it isn't really a solution anymore at all. So let's see if there's another one that's any different. I'm going to do another one because let's practice doing molar mass calculations and mass to mole conversions, right? Like I think I told you in the last chapter that, that's the mass to mole conversions are important. We're going to keep using them. So let's do another one of these just so that we can do a mass to mole conversion. If there's anything you come out of general chemistry with, you should be able to do mass mole conversions. So let's take a look. So this one, chemist prepares a solution of zinc nitrate. Now notice all those parentheses. The reason there's all those parentheses is they're just trying to say, look, zinc nitrate has this formula. So they put some parentheses around it. But then the inner parentheses are about the chemical formula, right? So the inner parentheses are telling you that there's 2 nitrates for every zinc. You're going to measure out 44.2 grams of zinc nitrate. 350 milliliters rounded to 3 sig figs, right? So same type of problem here. 350 is the volume, 44.2 grams is the mass. So when you do these problems, just make sure you're looking at what the units they give you, okay? So, our volume is 350 milliliters. I don't think they make volumetric flasks. I guess that you can have them made at what volume you want, but usually they're 200, 250, 500. So some of these are 300, 350, 400. You can maybe find them, but usually they're not in those volumes. I guess if you're in a rich lab where they have unlimited money, they might actually buy volumetric flasks at all different volumes that are available, just so that people don't have to change their calculations. So it's 44.2 grams of zinc nitrate. So zinc nitrate has this formula. Now, if you remember getting back to solubility at the beginning of the chapter, Nitrates are always soluble, right? Nitrates are soluble. So you can kind of, remind yourself that, yeah, this is going to dissolve. And actually, that's a pretty large mass. I don't know how many moles that's going to work out, but that's 44 grams. That's, how much is a sugar packet? A sugar packet is just like a few grams. I think it's 4 grams in a sugar packet, those little ones that you get at the cafes and stuff in the restaurants. So that's like 11 sugar packets. That's a lot of packets, but it will, it's nitrates are soluble, so it'll probably dissolve. So let's go through. Again, this is in grams. We want it to be in moles. So you're going to take your mass, which is in grams. You're going to divide it by the molar mass, and that's going to give you the moles. Right? I'll put abbreviation MOL, right? And that's what you want. And then, of course, the volume, we want that to be in liters. Okay. So zinc nitrate, oh my goodness, what is zinc? Zinc is like 63.59 or something. It's interesting. I actually don't generally do zinc. It's like 65.38. Okay, so copper is 63.55. Zinc is 65.38. Okay, so 65.38. That's your zinc. And then remember, you got this, you have this 2 outside the parentheses, so there's 2 nitrogens. So 2 times 14.01. And then you've got a total of 6 oxygens. So 6 times 16.00. Okay, or 15.9994 if you want to use that number. Okay, so the molar mass is 65.38 plus 28.02 plus 96. And that's 189.40. Okay, so that's your molar mass of zinc nitrate, right? So there's your zinc, there's your nitrogen, and then there's your oxygen. Okay, so 44.2 grams. And then 1 mole is 189.40 grams, right? So you're dividing it by that number. So 44.2 over 189.40. And you get point or decimal or not 23337. I'm putting some extra numbers in there. We'll round it at the end. Remember, you don't want to round it in each step. If you round your number multiple times, you get what's called a rounding error. So keep extra sig figs. Generally, most people would advise keep 1 extra sig fig in your intermediate steps. So if this one has 3 sig figs, just make sure you got at least 4. Now I'm keeping it, I generally err on the, safe side. So I'll put even an extra one. I'll put 5 and that's fine. So then what's our volume? 350 milliliters. Remember 350 ml, you can just kind of remember this. Just move it over 3 and you get 0.350 liters. Okay. So milli, do it 3. Centi is 2. Deci is 1. So if you have deci, move it over 1. If you have centi, move it over 2. If you have milli, move it over 3. Okay. But I've gone over a couple different ways you could do that conversion. So whichever way you're comfortable with. Okay. So there's your moles, there's your liters. So the molarity would be decimal 23337 decimal 350 liters. And then you get your moles per liter. Okay. So divide that by 0.35. And it's actually, this is a big number. This is I'm going to round it to 3, 667. Okay, so that's actually a pretty high concentration. It's probably getting close to the limit of how much zinc nitrate will dissolve, but that's pretty high. It's 2/3 of a molar, right? So almost it's 2/3 of a mole for every liter of the zinc nitrate. Okay. So that's the second type of problem for this section, is just making sure that you have the grams converted to moles, and then you're going to divide that by liters. Okay. Now, we're not going to see this in here, but if you do go on to take the next course, sometimes you'll have a problem where you might have, 1.25 millimoles. So you actually have millimoles. And then your volume, let's say your volume is 50 milliliters. Okay, I said this sort of at the beginning, but if that's the case, if they're both in milli, you don't have to do any conversions. Because the millis cancel. But why do prefixes cancel? Because they're just numbers, right? A milli is just it's a letter representing a number, right? So milli is representing 10 to the minus 3. And so if you have 50 times 10 to the minus 3 liters, right? So that's 50 milliliters. Well, then the 10 to the 3 just cancel. So that's why if it's the same prefix, you can cancel. In fact, if we were maybe clever, if I was being clever about it, if we had, 42 micromoles divided by 200 milliliters, to be clever about it, what you could have done is you could have converted this to millimoles. And then you'd have them both be in milli, right? And then you could cancel that. So that would actually be like, perhaps an easier way to do it. You just have to be sure you know how to convert micro to milli. You'd have to get that right. Or you could have converted this to micro and then canceled the micro, right? So either way, it's, there's many different ways to do these problems. It's up to you to be creative and enjoy your stuff. Enjoy your work. So let's see, we got one more type of problem. And that is dilution before we're done with this chapter. So I'm going to actually probably finish. Yeah, we'll finish about 15 minutes. So it looks good. So let me show you the dilution problem. But before I get into it, I want to talk a little bit about what dilution is. This is something you've done in your life many times. You're just not really aware that you're doing it, perhaps. Or maybe you are, but here we're going to do calculations. So dilution, oops, what happened here? Dilution is when you're taking, so this is really what you're doing. You're taking what's called a stock solution. A stock solution is something you get from a stock room. It's where you get the batch that's, you purchased from someone. It's called a stock. And then you're adding water to make a dilute solution. Okay, so let me show you an example. So imagine that I have, let's use a graduated cylinder because I'm getting tired of drawing the volumetric flasks. So imagine you have this graduated cylinder and, it's calibrated to 10 milliliters each line. I mean, 1 milliliter. So 1 milliliter, 2, 3, 4, 5. Okay, so let's say that I put in here 5 milliliters. So that's the meniscus of the water of the solution. So let's say that this is just a mixture of sugar and water. So let's say it's 0.1 mole, 0.1 molar sugar water. All right, so 0.1 molar, what that means is it's 0.10 moles of sugar in 1 liter of solution, right? Because that's what molarity is. If I say it's 0.1 molarity, 0.1 molar, what I mean is there's 0.1 moles of the solute for every liter of solution, right? That's what that means. Now imagine I don't have a liter in there, right? So remember, it's, you don't have to have a liter of water to have a density of water, right? You could have a little bit of water. It's still going to have the same density if you have a lot of water. So what I could do is I could just pour out one, you know, I'm going to actually, we'll take out 2 milliliters. I'm going to take out 2 milliliters and put it into another graduated cylinder. So I'm going to take out 2 milliliters. So that'll come up to here, right? So there's your 2 ml. That's the 2 ml that I transferred over. Let me put it in a different color. That's the 2 that I just pulled out of there. And then suppose what I did was I added more water. I added another 2 milliliters of water. Right? What would happen to the concentration of the sugar in this mixture now? It would change, right? Because it had a concentration here of 0.10, but now I've doubled the amount of water. So this is what happens. When you double the amount of water, the concentration goes down. It goes down by a factor of 2. So now it would be half as much. So now it would be 0.05 molar, right? It would be half of 0.10. And half of 0.10 is 0.05. Because I added 2 milliliters of this and 2 milliliters of water to give me a total of 4 milliliters, right? So that's dilution. You're taking the stock solution that has a higher concentration. You're taking some of the stock and you're adding water to it to give yourself a lower concentration. Okay. Now there's a very simple relation here. And that is the molarity of the stock solution, S for stock, times the volume of the stock that you take out. So the volume of that solution you're taking out. So it's not the whole solution, it's just what you're taking out, is equal to the molarity of the new solution, the dilute solution. This is dilute, and this is stock, times the total volume of the dilute solution, D for dilute. Okay, so this is the stock solution. This is the stock solution that you're taking out. So it's, you know, I didn't take out all of it. I just took out some of it. So it's the amount you're taking out. And then this is the new solution, the dilute solution over here, times the total volume here. Total meaning what's the amount of the dilute of the stock that I took out plus the water that I'm adding in, that total volume. In this case, it would be 4 milliliters, right? And if you put it in, you'll get the right answer. If I took 2 milliliters out, that would be 2 milliliters. The stock was 0.10 molar. So now if this is 4 milliliters, if you take 0.10 times 2, you get 0.2. Divide that by 4, you get 0.05. And so the molarity of this dilute solution would be 0.05. So that's the nice relationship you can use. It's sometimes called the dilution formula. Okay, so let me show you an example. Okay, so a chemist must dilute 79.5 milliliters of 310 millimolar, right? See the milli? Aqueous potassium permanganate solution until the concentration falls to 42.0 millimolar. He'll do this by adding distilled water to the solution until it reaches a certain final volume. Calculate this final volume in liters, okay? So let me show you what's actually happening. Okay. Okay. So what they're saying is you've got a stock solution. They're not going to tell you how much of the total stock you have, or, you know, it depends how you interpret it, I guess. What they're telling you is he's going to take 79.5 milliliters of this stock solution. Okay, so that's a volume. They tell you the concentration, 310 millimolar. Okay, they're going to take this solution and add it to water. Now, it's up to you how you want to interpret. Either they add the water to it or you add it to the water. But they're not telling you the total volume. They're not telling you. They're asking you, what is the volume of the dilute solution? In liters. Okay, volume. So they're asking you for the volume. They do give you one piece of information, is that after you do the dilution, this is 42.0 millimolar. Okay. So one way to think about this is in terms of proportionalities. So if you think about it, this is 310 millimolar, right? So if you were to add, you know, let's just look at this like just really rough estimates. We're just going to estimate here. I could claim that this is, you know, it's about 80 milliliters, right? That's pretty close to 80. And the concentration is about 300 millimolar. Okay. Now, in terms of proportionalities, here's what I could do. I could say, look, I'm going to add another 80 milliliters of water to give me a total 160, right? So I'm doubling the amount of water. The concentration would go down by a factor of 2, right? If you double the water, the concentration goes down by 2. So this would now be 150 millimolar, right? Now, suppose I doubled it again. So instead of 160, I added another 160, and that would give me a total of 320, right? Now this would go down again by a factor of 2, and it would be down to 75 millimolar. Okay. So what that's telling me is that really I'm going to have a total volume of 320 milliliters to get it down to 75. Okay. If I want to get it down to 42, I'm going to have to add even more water. So you know your total is going to be like over 300 milliliters. So that's just to kind of give you an idea of the proportionality. But here's how we can do it. The molarity of the stock solution, we have that. That's 310 millimolar times the volume of the stock that you're going to use. And they tell you you're going to use 79.5 milliliters. Okay. That is equal to the molarity of the dilute solution, which they tell you 42. So that's equal to 42.0 millimolar times the volume of the dilute solution. The volume of the dilute, we don't know, right? So I'm just going to write volume of dilute. We don't know what that is, but that's what it's asking us to do. So if we want to find V, all we have to do is divide both sides by 42 millimolar, right? If I divide this side by 42 and I divide this side by 42, now the 42s cancel and you've got the volume of the dilute solution over here on the right, okay? And then you say, well, okay, let's do the dimensional analysis. Millimolar divided by millimolar, that's done. That's going to give us the volume in milliliters. Okay, so let's do the arithmetic. 310 times 79.5 divided by 42.0, and you get, oh, that doesn't, yeah, that's right. I'm sorry, I almost talked myself out of the right answer. 587 milliliters. And that's equal to the volume of the dilute solution. Now, they did ask us to convert it to liters. So that's something we can do. I'll do it up here. So I'm going to take 587. And a couple different ways you could do it. One way would be to say, hey, a liter is 1,000 milliliters. So you're just going to divide it by 1,000. This is milliliters, sorry. And then your milliliters cancel and you get 0.587. That'll work. So 0.587, okay? And so, you know, almost 0.6 of a liter, okay? So what that tells you is your total volume is 587 mil. I'm going to put in milliliters over here. So then you ask yourself this, now in this problem, they didn't ask you to do this, but you could ask yourself, how much water did we add? And the answer would be that if the total is 587 and the amount of the stock solution we put in is 79.5, the amount of water you added is just the difference, right? Like you got to have, you have your 79.5 here. So then the rest of it, it's got to add up to 587. So whatever that works out to, what, 507.5? Okay, so that means we must have added 507.5. Now the question doesn't ask you to figure that out, but if we wanted to know, that's what we would get. Now it turns out it's not exactly 507.5 because what happens is when you have solutes in water, the solutes make the volumes no longer additive. So 1 milliliter plus 1 milliliter is not necessarily 2 if one of them has salt in it and the other one doesn't. The dilution effect of the solute affects the volume, not by much, less than 1%, but it does affect it a little bit. So if we want to be real accurate in our calculations, we would take that into account. Okay, let's look at one more. A chemist makes 670 milliliters of potassium dichromate. Working solution. Okay, working solution is the stock solution, just for your terminology. Okay, I'm sorry, careful. A chemist makes 670 milliliters of potassium dichromate working solution by adding distilled water to the stock. So I was wrong. If you're adding water to the stock, that gives you the dilute solution. So in their language, the working solution is the dilute solution. Okay. Calculate the concentration of the working solution. So that's the dilute solution, concentration of the dilute solution. Okay. So your volume of the stock is 670. Your concentration, I'm sorry. 670 is the working solution, which is the dilute solution. So the volume of your dilute solution is 670. You're adding water to 260 milliliters of 54.3 millimolar stock. So this 260 milliliters is the stock volume, and the 54.3 millimolar is the stock concentration. Okay. And then they're asking you for the concentration of the working solution, the dilute solution. I don't know why they got to call it working. Some people just like to change words. Okay, so let's take a look at this one. So you got 670 milliliters of potassium dichromate working solution. By adding 260 milliliters, and I'm just going to write that this is stock solution. They tell you this is the stock solution. And then they tell you that it's 54.3 millimolar stock solution. And then they ask you for the concentration of the working solution. Okay, so let's take a look at that. So we're going to say in this case, working is dilute. Okay, come back to the dilution equation. Yeah, we'll call it working, W, right? We want the concentration of the working solution. So that's this right there. So that means you just got to divide both sides by the volume. So let's just put our numbers in. Our stock solution is 54.3. Our volume of the stock is 260. And then our volume of the working solution is 670. And then you can kind of check yourself. If it goes up, that doesn't make sense. The stock solution can't get more concentrated by adding water. It's got to get less concentrated. So if your answer is bigger, if it's greater than 54.3 at the end, then there's a problem with that. Okay. So 54.3 times 260 divided by 670, and you get, was that 21? So 21.1, and then that's millimolar. So there's your concentration. So that's the concentration of your working solution. It is more concentrated than the stock, less concentrated than the stock solution. That makes sense. This should be less concentrated. You cannot make sugar more concentrated by adding more water to it. Adding water to it will make it less concentrated. So essentially what happened was, here's your stock, 260 ml. Here's your working. And the working is 670 ml. Okay, and there you go. All right. Just one brief mention. You can actually use different symbols. So I could say C1 for the concentration of the stock times V1, which is the volume of the stock, is equal to C2, which is the concentration of the dilute or the working, times the volume of the dilute or the working. C1 V1 equals C2 V2, or you can use M1 V1 equals M2 V2. Doesn't matter what symbols you use for these, you just got to keep it straight in your head which ones you're using. But many different symbols are used for these. Okay, and there you go. So that's the dilution. That's the end of section 5, which is the end of chapter 4. So good luck getting through all of these. And on Monday is a federal holiday, but I am going to go ahead and make a 1-hour video discussing the beginnings of chapter 5. So I will be online at 9 o'clock on Monday. So if you want to join, feel free to. And then I'll have that video posted on Monday by Monday afternoon. And then on Tuesday is the section B is going to be meeting on campus. So, so if you don't watch the video on Monday, you can watch it on Tuesday. And then on Wednesday, we'll come back and we'll keep working on it. Okay. So this chapter 5 that we're going to cover is about energy. So we'll start working on energy in chapter 5. It's an exciting chapter. And then we'll keep moving along. Okay. So have a great day. Take care.